Dear students, myself Kiran MP. I am working as assistant professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar. I welcome all of you for today's session on functions. So, first let me have a look at agenda of this session. In this session, first I am going to give you an introduction to what is known as functions. Once you have been introduced to functions, then we will look at some types of functions such as plain functions, identity functions, and constant functions. Apart from listed three types of functions, there are some more functions such as one-to-one, on-to, one-to-one correspondence, which we are going to discuss in the subsequent sessions. Now, let me have a look at what do we mean by function. So, assume that you have two sets, A and B, and this A and B are non-empty sets. Then you know a relation from A to B, right? Already we have studied relation previous session. So what actually relation from A to B is nothing but a subset of A cross B. I repeat, a relation from A to B is nothing but subset of A cross B, where we see some elements of set A will be related to some elements of set B. Also, you remember, in relation from A to B, the same element of set A might be related to more than one element of set B. I repeat, in relation from A to B, the same element of set A might be related to more than one element of set B. Also, in relation from A to B, there are some elements in set A which might have not been related to any of the element of set B. I repeat, also in relation from A to B, there might exist some elements in set A which have not been related to any of the elements of set B. Is it? So, we know that if a set A contains m elements and set B contains n elements, A cross B will have m into n elements. The number of subsets of A cross B is nothing but 2 power mn. All these 2 power mn subsets of A cross B we call a relation from A to B. Got it? Of these 2 power mn relations, we need to look at few relations. Means you can point out some relations in which all the elements of set A will be related to exactly one element of set B. I repeat, among 2 power mn relations from A to B, we can observe few relations in which all elements of set A will be related to exactly one element of set B. And such relations we call a function from A to B. Got it? Clear? So what actually functions from A to B is nothing but a relation from A to B in which all elements of set A are related to exactly one element of set B. Clear? So the function we sometimes refer it as mapping. Okay, clear? So suppose let me say A is an element in set A which is related to B, an element of set B. Okay, got it? In a function, then we represent that an ordered pair A comma B belongs to function F. Okay, I mean to say if F is a function, okay, F is some function, and for that particular function F, an input is an element of set A, say an element A. Okay, so we are going to get an output, okay, from this function which is an element of set B, and this is written as B equals f of A. Clear? I repeat, see, for this function f, okay, which is a relation from A to B, right? Suppose an ordered pair A comma B exists. Okay, it means A is an input to function f and B is an output of this function for an input A, and this is written as B equals f of A. So hope all of you came to know about what is function. So one thing you need to remember always, all functions are relations, but all relations need not be functions. Clear? I mean to say all functions from A to B are relations from A to B, but all relations from A to B need not be function from A to B. Now we'll look at some terminologies and functions. Okay, see, if A is an input to function f and B is its output, we represent it as B equals f of A, right? So this B, an element of set B, we call an image for an element A in set A. Got it? I mean to say here, B is an element of set B to which an element A of set A is related. We call an image of A. Got it? And A with respect to an element B, I will call as a pre-image under this particular function f. Okay, I repeat, in case if B equals f of A, we call B an element B, okay, as an image of A, and an element A we refer as pre-image of B, okay, under this function f. So now how will denote a function? Means a function f from A to B is denoted as f colon A implies B. Okay, a function from A to B is denoted as f colon A implies B. And there are something known as domain of a function and codomain of a function. Okay, what actually domain and codomain? Let me tell you. If f is function from A to B, okay, if f is function from A to B, then the set A we call domain of function f. Okay, I repeat, in function f from A to B, the set A is called domain of function and set B is called codomain of function. Okay. Next, okay, see what I said function. It's a relation from A to B in which all elements of domain, that is set A, are related to exactly one element of codomain, that is set B. Okay, so in functions what we can observe is that not all elements of set B, that is codomain, appears as an image. I mean, there might exist some element in codomain which might have not appeared at all as an image. Okay, I mean to say there exist few elements in codomain which might have not appeared as an image at all. Okay, and those elements of codomain which have appeared at least once as an image, okay, collectively we call as a range. I'll tell you. See, in codomain, not all elements appear as an image, and those elements of codomain which appears at least once as an image, I will collectively call them to be range. Okay, so let me tell you. So what is range of function means? I repeat, listen. What is range of function? Range of function f is nothing but set of all those elements of codomain. Set of all those elements of codomain which appears at least once as an image. Okay, hope you got to know. So let me repeat once again. So range of function f from A to B is nothing but set of all those elements of codomain B which appears at least once as an image under function f. Okay, clear? So now you are familiar with functions. You know what is an image, what is pre-image. You know what is domain, what is codomain. Also, you know what is range of function. So I repeat, range of function is nothing but set of all those elements of codomain B which appears at least once as an image. Now let me have a look at one example. Okay, see here we have given two sets labeled A and B. In set A there are four elements A, B, C, D, and in set B there are three elements W, X, Y. Got it? So I have given some three relations from A to B, and I need to check whether these three relations from A to B, all three are functions from A to B, or is there any relation among these three which is not a function from A to B. Okay, so I repeat, in this example I have given two sets. One is set A with the four elements A, comma B, comma C, comma D. And one more is set B with three elements W, comma X, comma Y. And I have given three relations from A to B. Okay. Now the question is, you need to check of these three relations from A to B as any relation as a function from A to B. Okay. So let me observe it, analyze. So you know, right? What is function? A function f from A to B. I repeat, a function f from A to B as a relation from A to B in which all elements of set A should be related. I repeat, all elements of set A should be related to exactly one element of set B. Is it? So now let me observe, analyze the first relation from A to B. Okay. In the first relation from A to B, which consists of three ordered pairs. The first ordered pair A, W. The second ordered pair again A, W. Let it be B, W. Assume there's slight correction. And first relation from A to B, the first order is A, W. Okay, the second ordered pair is B, W, and third ordered pair is C, W. Okay. So in first relation from A to B, okay, after making correction second ordered pair, that is as a B, W, okay, we find an element D of set A is not related to any element of set B. I repeat, in first relation from A to B, an element D of set A, that is domain A, is not related to any element of set B, that is codomain B. So the first relation doesn't satisfy the condition of function. Yes, the first relation is not a function from A to B. Okay, clear? So now let me have a look at the second relation from A to B. So in second relation from A to B, there are four ordered pairs. The first ordered pair is A, W. The second ordered pair is B, W. The third ordered pair is C, W, and the fourth ordered pair is D, Y. D, Y. Now let me analyze the second relation consisting four ordered pairs A, W, B, W, C, W, and D, Y as a function or not. So function definition states all elements of domain should be mapped to exactly one element of codomain. And this condition is satisfied by the second relation from A to B. I mean, all elements of domain A, B, C, D are mapped to exactly one element of codomain B. So it's a function. Now let me have a look at third relation. Okay, and third relation from A to B, there are three ordered pairs: A, W, B, W, and C, W. And this third relation from A to B, an element D of domain A is not mapped to any of the element of codomain B. I repeat, In third relation from A to B, an element D of domain A is not mapped to any element of codomain B. So third relation from A to B is not a function 2. So conclusion is that of these three relations from A to B, only the second relation is a function from A to B, whereas the first and third relations are just a relations from A to B but not a function from A to B. Now let me analyze, okay, how many functions from A to B might be possible. Also, how many functions from B to A might be possible. Okay, suppose let me assume the size of set A is M and size of set B is. Now let me analyze the number of functions that are possible from any domain to codomain. Suppose A and B are two given sets with the size of A to be M and size of B to be N. Okay, so the number of functions that are possible from A to B is found to be n power m, and the number of functions from B to A is m power n. Let me justify the number of functions from A to B to be n power m. See here, in set A there are m elements, okay, and we know that in a function all elements of domain say A should be related to one element of set B, that is codomain. So for each element of set A, that is domain, in this case there are n ways, okay, to choose an element in B as an image. I repeat, for each element of set A, there are n ways of choosing an element of B as an image. Got it? Since there are m elements in set A, so applying the product rule, we are going to get n power m functions from A to B. Clear? So now let me have a look at example. Here we are given two sets A with three elements 1, 2, 3, and set B with three elements 2, 4, 5. So according to the formula we have just obtained for the number of functions from A to B, which is n power m, implies the number of functions from A to B is 3 power 3, that is 27. Similarly, the number of functions from B to A is again 3 power 3 equals 27. Now let me look at some types of functions, okay. The first function here I am going to tell you about is what is known as identity function, okay. You know binary relation, right? So what is binary relation? An element of set is related to an element of its own set. Such relation we call binary relation, right? Means relation from A to A is known as binary relation on A. Got it? So for some of the binary relations might be functions from A to A. Okay, and that relation, I mean relation from A to A. Okay, I mean a function from A to A is said to be identity function if all the elements of set A is related to itself. I repeat, a function f from A to A is known as identity function or identity mapping on A if all elements of set A is mapped to itself. That is, f of A equals A for every A belongs to set A. So example, look at example 3. Set A consists 3 elements 1, 2, 3, and a subset of A cross A consisting 3 ordered pairs 1, 1, 2, 2, 3, 3. It's an identity function from A to A. Got it? So what is identity function? It's a function from A to A where all elements of domain A are related to or mapped to itself. Okay. Now let me have a look at what is known as constant function. See, assume f is a function from A to B. Okay. Assume f is a function from A to B, and if all the elements of domain A are mapped to same element of set B, that is codomain, okay, then we call such a function f from A to B as constant function. I repeat, a function f from A to B is known as constant function if all elements of its domain A are mapped to same element of its codomain B. Okay, so look at an example. See here, G is a function defined on A with 3 elements 1, 2, 3. Okay, here all elements 1, 2, 3 are mapped to element 2. Observe, in function G from A to A, all 3 elements 1, 2, 3 are mapped to same element 2. Hence we call it's a constant function. So clear with identity function and constant function, right? So in identity function, all elements of domain are mapped to itself. In constant function, all elements of domain are mapped to same element of codomain. Now, let me have a look at some mathematical functions, okay, known as floor function, ceiling function. Okay, let me tell you. See, floor function, it's a mapping from real numbers to integers. I repeat, floor function is a mapping from real numbers to integers. I mean, for floor function, input is a real number and the output is an integer. I repeat, floor function is a mapping from real numbers to integers. Input to floor function is real number and output is an integer. So what is an output of flow function, okay, for a particular real number. Okay, say x. Okay, for a real number x, the output is the greatest integer among the least or equivalent to x. I repeat, for input x, which is a real number for a flow function f, the output is the greatest integer among the least or equivalent to x. Say an example, flow function of 1.4. Okay, so 1.4 is a real number, right? So you list all integers less than or equal to 1.4. I repeat, you list all integers which are less than or equal to 1.4. So when you list the first least integer is 1, then 0, minus 1, minus 2, minus 3, so and so on. So of this the greatest is 1. That's an answer. Got it? So what is flow function? It's a mapping from real numbers to integers, and for an input x, which is a real number, the output is the greatest integer among the least or equivalent to x. Now let me have a look at ceiling function. Ceiling function is similar to flow function, means mapping from real numbers to integers. Okay, I mean for ceiling function, again the input is x, which is a real number. The output in this case is the least integer among the greatest or equivalent to x. I repeat, ceiling function is again mapping from real numbers to integers. For ceiling function f, an input is x, which is a real number. The output is an integer, which is the least integer among the greatest or equivalent to x. So look at an example, ceiling function of 2.9. Okay, you list all integers greater than or equal to 2.9. You list all integers greater than or equivalent to 2.9. The first greatest integer is 3, right? Then 4, 5, 6, 7, 8, so and so on. Of this integers, the least is 3, and that's an answer. Clear? So now let me look at some examples which uses a combination of flow function and ceiling function. In first example, that is flow function of 7.1 plus 8.2. 7.1 plus 8.2 is nothing but 15.3. 7.1 plus 8.2 is nothing but 15.3. It's a flow function, right? So list all integers lesser than or equivalent to 15. Lesser than or equivalent to 15. Sorry, lesser than or equivalent to 15.3. Sorry, I repeat, list all integers lesser than or equivalent to 15.3. So integers lesser than or equivalent to 15.3 are 15, 14, 13, 12, 11, 10, so and so on. Of this, the greatest integer is 15, and that's the answer. Now, let me have a look at second example. It's the flow function of 3.2 minus the flow function of 2.5. So first let me obtain the value of flow function of 3.2 and flow function of 2.5. To compute flow function of 3.2, let me list all integers lesser than or equivalent to 3.2. They are 3, 2, 1, 0, minus 1, minus 2, so and so on. Of this, the greatest is 3, and that's the answer for flow function of 3.2. Similarly, for flow function of 2.5, I will list all integers less than or equivalent to 2.5. They are 2, 1, 0, minus 1, minus 2, so and so on. Of this, the greatest integer is 2. And that's the value of flow function of 2.5. So 3 minus 2, obviously it's 1. Very clear. Okay, let me have a look at third example. Okay, it's flow function of 5.3 into ceiling function of 8.1. Okay, just a small correction in third function. Okay, third example is not subtraction, it's a product. Okay, just a small correction, it's a product of flow function of 5.3 and ceiling function of 8.1. So first let me compute the flow function of 5.3 value and the ceiling function of 8.1 value. So to compute flow function of 5.3, I will list all integers lesser than or equivalent to 5.3. They are 5, 4, they are just a small correction. Okay, it's actually ceiling function of 5.3 and flow function of 8.1. A small correction in third example. For 5.3 you should have computed the ceiling function, and for 8.1 we should have applied the flow function. Okay, just a small correction, just replace flow function of 5.3 with ceiling function, and ceiling function of 8.1 is flow function. Okay, and the subtraction is product. Then we are going to get 6 into 8, which is nothing but 48. Okay, so now in this session we are just introduced you to what is known as function, also some concepts such as image, pre-image, domain, codomain, range of functions. Also we have seen how to compute the number of functions that are possible from any domain to codomain. Okay, I mean to say you are now able to determine the number of functions from A to B that are possible. Then we had a discussion about a few basic type of functions such as identity functions, constant functions, flow functions, ceiling functions. Okay, with this let me wind up my session. Thank you for listening.